Hi everyone, this video covers section 4.3 dealing with maxima and minima, highest points and lowest points on functions. The word extrema that you see there, that is just the more general term for maxima and minima. And maxima and minima, that's just the plural of maximum and minimum. Okay, so we have highest and lowest points on functions that we're dealing with in this section. And we can see here in this first graph, f of x equals x squared plus 1. If we're talking about the interval from negative infinity to positive infinity, then we know that this parabola keeps on going upward in both directions. So on that open interval from negative infinity to positive infinity, we have no absolute maximum, but we definitely do have an absolute minimum, okay, at the point 0, 1, or when x is 0, the y coordinate is 1. If we were to just talk about the closed interval, say from, I don't know, -1 to +1, then we would still have that same absolute minimum, okay, but then if it were a closed interval, we would have two highest points on the graph also at -1 and at +1 if we were to talk about the closed interval. But that's what we're going to be covering in this section, is how to find highest and lowest points on functions. If I'm looking at a graph, it's hopefully fairly straightforward, but how do I do that using just the function itself and not a graph? So first we will define what an absolute maximum and minimum is. So this is a super formal definition. Let f be a function defined over an interval I, and c is a number contained in that interval. We say that f has an absolute maximum on I if f of c is greater than or equal to f of x for all x in I. Okay, that's super formal. But what this inequality here means is that f of c, that y coordinate, is the highest point over every other y coordinate in the interval. And then for absolute minimum, f of c is the lowest point over every y coordinate in that interval. Okay, that's the way that we've formally define it. I mean, you can tell by looking at a graph what the highest and lowest point is. Well, this is how we have to write that down. Here's a couple of graphs. There's 6 to be specific. You can pause the video if you want and think about visually, do you see absolute max or min on these different functions? Okay, so the first one, f of x equals x cubed. You can tell kind of by looking at that this first one does not have any absolute maximum and it does not have any absolute minimum. The second one there, f of x equals 1 over x squared plus 1. There is a maximum right there when x is 0, y is 1, but there is no minimum on that function. Just like that. There we go. The next one, f of x equals the cosine of x. That one we do have one absolute maximum that we can see, actually 3 absolute maximums that we can see, and 2 absolute minimums. Here are my absolute maximums. These 2 are my absolute minimums, and if you know stuff about your cosine curve, you might know where they are. 0, 2 pi, 4 pi, 6 pi, plus or minus, because that cosine curve keeps repeating. We keep extending out further, and then the minimums are at pi and at all the odd pi's. Okay, and the absolute maximum, the y coordinate is +1, and the absolute minimum, the y coordinate is -1. Next, we have this piecewise function. We can see here's a high point, but right there is a higher point. The absolute maximum is at when x is 0, the y coordinate is 2, and you might think that's an absolute minimum, but because the circle's not filled in there, we technically don't ever get to that point 2, -2, so we actually have no absolute minimum. All right. The next one, absolute maximum, is up here when x is 4, y is 4, and the minimum, not there, the minimum is right here when x is 2, y is 0. And our last one, we definitely have an absolute minimum, okay, but that graph keeps extending up indefinitely, so there is no absolute maximum. Okay, so identifying them from graphs, not terrible, all right? Where it gets a little bit more challenging, right, is how do we find maximum and minimum values when we're just working with the function itself? Before we get to that, though, we have a couple more definitions. The first being local. So instead of absolute, we have local extrema, and then critical points we'll define on the next slide. All right, so local extrema are like interior maximum and minimum values, not necessarily the highest point on the function or the lowest, but where does it reach a peak or a valley. A local maximum is defined as the point C inside of some interval I, such that I is contained in the domain of f, and f of c is greater than or equal to f of x. That means that this y-coordinate is bigger than that y-coordinate for all x in that interval. So some open interval. So like, for example, in this interval of x coordinates, that x coordinate is the highest point among all of them. Or in this interval of x coordinates, this x coordinate right there has the lowest y value among all of them. Okay, it's not the whole interval on which the function is defined. It's just some interval containing the point C. All right, and then the second part of the definition, a local minimum, f of c is less than or equal to f of x for all x in that interval. Okay, and here we have another local maximum on that function. This y-coordinate is higher than all of the other y-coordinates around it. Actually, that y-coordinate is the highest on the whole function, so this would be a local maximum as well as an absolute maximum. Now, those local max-min points, those are called critical points. Okay, critical points where we have our horizontal tangent line, we find them by setting the derivative equal to 0. We've already talked about horizontal tangent lines in the past. Now we're going to find them by taking a derivative of a function, setting it equal to 0, and those are called critical points, and those are our possible local max-min points. Okay, so let's find some critical points for each of these three functions here. So I'll start with a, and that function is f of x is equal to 1/3 x cubed minus 5/2 x squared plus 4x. So the steps here are I take the derivative, x cubed minus 5x plus 4. Oops, x squared that should be, not cubed. There we go. And it's minus 5x plus 4. Like that. So that's step one, take the derivative, hopefully correctly, and then we set it equal to 0. This quadratic I can solve by factoring. X minus 4 times x minus 1 equals 0. So x is equal to 4 and positive 1. And you can go to OpenStax or use some website like wolframalpha.com to take a look at this graph if you want to. But I'm going to label and let you know that x equals 1 is a local maximum. And x equals 4, that is a local minimum. We'll have some more techniques later on in a later section where we find local max and local min in a more technical way. All right, so that is it for A. Moving on to B, I want to take the derivative of that function first, but let me write it down. F of x is x squared minus 1, all of that to the third power. So the derivative, bring the exponent down, keep the inside the same. I'm using the chain rule. Subtract 1 from the exponent and multiply by the derivative of the inside. Okay, so we'll set that equal to 0. And then I can divide both sides of that equation by 6, right? So if I do, I'm left with x times x squared minus 1 squared equals 0, right? I just divided left and right side by 6 to cancel out the 3 and the 2. In order to solve this, okay, I'm going to split this apart because this is a product, so I can set each factor equal to 0, that first one, and then this other one, x squared minus 1 squared equals 0, and then just focus on the one on the right, because the one on the left is done. Take the square root of both sides, and I have x squared minus 1 equals 0, and then factor into x plus 1, 1, times x minus 1, and we can see that we have x equals 0, x equals 1, and x equals -1 are all critical points. But, and you should go to the graph on OpenStax, or again, type it in a website like wolframalpha.com, x equals 0, that one is a local minimum. But at 1 and -1, the function doesn't have a local max or a local min. It just does, it has a little funny bit of a shape to it. Take a look at it. I'm not going to graph it for you here. Just because we find a critical point and it could be a local max or a local min does not guarantee that it is. Let me scroll up to give myself some more space for part C. And I'm going to rewrite the problem first. It is f of x equals 4x over 1 plus x squared. Now we would use the quotient rule to take this derivative. I am going to give you the simplified derivative. We've had lots of practice with the quotient rule, so I'm not going to go through those steps. That'll just make the video longer. 1 plus x squared equal, there we go. All right, so that is my derivative. All right, and if I set that derivative equal to 0, okay, what we do when I have a fraction equal to 0, ask yourself, when is a fraction equal to 0? The answer is when the numerator is 0. Oops, that should be 4 minus 4x squared. It would help if I didn't make mistakes. Sorry about that. Okay, what I was saying is a fraction is equal to 0 when the numerator is 0. So I'm just going to take that numerator, 4 minus 4x squared, and set it equal to 0. If I factor here, we have 4 times 1 minus x squared equals 0. And that factors into the same way that x squared minus 1 does. This is 1 minus x times 1 plus x equals 0. The 4 I could keep tagging along. Ultimately, it's going to cancel out. Just divide by 4 on both sides. It's just a constant. It doesn't give me any more zeros. But we do get 2 zeros. We get x equals 1 is a critical point, and x equals -1. These are our critical points. Maybe I should have written that with the previous 2 examples, but I didn't. Okay, so that's our critical point. All right, and then take a look at the graph. It would be a good idea. At +1, we have a local maximum. And at -1, we have a local minimum. All right, that's how that works. Now we get to the meat of the section. What we just talked about, that was all build-up leading to this. How do we find absolute extrema over a closed interval? First, the theorem states that if I have a continuous function over some bounded interval I, the absolute maximum and the absolute minimum must occur either at the endpoints or at the critical points. Okay, and that's what we're going to do in the last couple examples. We're going to find absolute extrema, absolute max, absolute min, over a closed interval. And the steps that will follow are going to be to evaluate at the endpoints, find the critical points, evaluate them in F, and then compare all of our answers to find the highest and the lowest, the absolute extrema for that function. Here are the 2 examples that we'll do. All right, step 1 on problem number 1 is to evaluate f at the endpoints. So f of x is equal to -x squared plus 3x minus 2, and the interval is 1, 3. We'll take f of 1 and f of 3. -1 squared plus 3 times 1 minus 2. And -3 squared plus 3 times 3 minus 2. When you substitute in 1, you get 0. When you substitute in 3, you get -2. Okay, I'm going to star those because I need to look back at them when I'm done with the next step. Okay, and I could even actually, maybe I'll write them as coordinates. 1, 0 and 3, -2. You don't have to, but maybe it'll be helpful. All right, now step 2, we're going to take the derivative, -2x plus 3, and set it equal to 0. if I add 2x, 2x is equal to 3, x is equal to 3 halves, also known as 1.5, which is inside of our interval from 1 to 3. All right, so then we'll take and evaluate f of 3 halves, f of, not f prime, the original function, because I want to get y coordinates. If you want y coordinates, you go back to the original function. If you want slopes, you plug into the derivative. F of 3 halves is negative 3 halves squared plus 3 times 3 halves minus 2, and that simplifies to 1/4. F of 3 halves is 1/4. Check it in your calculator. You should get 1/4. So that gives me a third point now of 3 over 2, comma, 1/4. All right, so now let's analyze. What is the highest point on my function over this closed interval? Well, the biggest y coordinate is that one right there. This is the absolute maximum. And the lowest point on my function right there, this is the absolute minimum. Like that. Okay, that's the goal, is to find those two things. Absolute max, absolute min over our closed interval. Now let's look at b. In part b, my function is, let's go with white to separate. Part b, my function is f of x is equal to x squared minus 3x to the 2/3 power. So same first step. I want to evaluate it at the endpoints of my interval, which are 0 and 2. So 0 squared minus 3 times 0 to the 2/3 power, that is 0. And then 2 squared minus 3 times 2 to the 2/3 power. That's one you should definitely just type it into your calculator. Make sure you put parentheses around the exponent. So 2 raised to the parentheses, 2/3 power. And you should get negative 0.762. Oops, 0.762. All right, so that's the first two pieces of information that we get. To negative 0.762. Right, like that. I'm going to star them so I know where to look when I finish the next step. Step 2 is to take the derivative. The derivative of x squared is 2x, and the derivative of 3x to the 2/3 power is 2x to the negative 1/3 power. Okay, the 2/3 comes down, the 3's cancel out. The new exponent, 2/3 minus 1 whole, is negative 1/3. All right, so we're going to set that equal to 0 and solve for x. When we're solving equations and we have that negative exponent there, it'll be better if we write it as a fraction. So throw that x to the negative 1/3 down in the denominator where it belongs. That's what the negative exponent does, drops it down to the denominator. So we have that this is equal to 0. And there's a couple of different ways that I could show you to solve this. One that I think will be clearest, hopefully, is to leave my 2x on the left-hand side, write my 2 over x to the 1/3 power on the right-hand side. And then I want to just clear that fraction. So I'm going to multiply x to the 1/3 power on both sides. And what that's going to do is this exponent and that exponent are going to add together. So on the left-hand side, I have 2x to the 4/3 power, and on the right-hand side, I have 2. Let's go up here. I can divide both sides by 2. X to the 4/3 power is equal to 1. And that may seem simple enough. If you take if you cancel out the exponent, right, the 1 isn't going to change. But actually, x can be positive or negative 1. Positive or negative 1. Okay, because negative 1 to the 4th power, the 4 is up in the numerator, negative 1 to the 4th power is also positive 1. All right, so that gives me 2 more points to test in my original function. And I'm not going to write all of these values out, but if I check f of -1, I'm not going to write the whole expansion out for f of -1 and f of +1. But I will tell you what you get for the y coordinates. For f of +1, you should get -2. And f of -1 does have an answer, but let's not worry about that. We don't have to waste our time on that. Why? It's not in the interval. We don't care about -1. It's not between 0 and 2. Okay, so going back to the other 2 points that we have, now our third point is 1, -2. We have 3 points here. 2 at the endpoints and 1 critical point. Which one is the absolute max? The highest y coordinate is right there. Absolute maximum. And which one is the absolute min? The lowest y coordinate is right there. Absolute minimum. All right, that's how it works. Go work on some homework. Let me know if you run into any problems. If you want to see another example, I'm happy to do one out for you. Let me know. Thank you very much for listening. Have a wonderful day.